Were India's EVMs really tamper-proof? We're about to find out. When Harry and his engineers opened the machine, this is what they saw. And when we later released pictures like these, it was the first time that citizens in India were ever able to see how the machine counting their votes really worked. I don't know what the big secret was, why the Election Commission wouldn't let anyone see, because it's actually really simple. Inside, there's a microcontroller, a basic CPU. It includes a copy of the election firmware, the software that runs the elections, and that software is programmed into the chip at the factory and can't later be changed or read out. In addition, there are these smaller chips. These are EEPROM memory chips, which store redundant copies of the votes. Those large black things with the white pieces sticking out, those are just the switches that are underneath the buttons on the front of the control unit. So in addition to the main logic board in the control unit, there's the only other thing is this smaller daughter board, which is the 7-segment LEDs that show the election results during counting. And you could barely build a simpler board. It's just LEDs and wires and connected to the main board via that short ribbon cable you see on the right. That blue thing, you might be wondering what that is at the bottom of the shot. That's actually a speaker. That's the thing that beeps every time someone votes. And after Rob and I got to Hyderabad, where Harry and his team of engineers were studying the machines, we were doing tests on the machine with the case open. And when we did these tests at night, the noise from the speaker was just so loud that if we had the windows open because of the heat, it would wake up dogs all over the neighborhood, which would start barking and raise suspicion. This project we were working on in secret. We didn't want to draw any other attention, so we just naturally covered the speaker with a piece of tape. This machine, though, the design is so simple. And when you're thinking about how someone might try to attack it, that's going to involve attacks at a variety of levels of sophistication. Before I explain to you the ways we devised to attack the machine, I'd like you to try to think for yourself, what are some of the things that could go wrong? How could criminals cheat on a real Indian EVM? So there are a lot of ways that you could try to tamper with an EVM and make it change votes. My attention was first drawn to this part, the display board, since it's probably the simplest part of the EVM design. And initially, I only found out that I was going to be able to go to India and get to be part of a team with access to one of these machines about 3 days before I left. And so I had to come up with a really simple attack to try to manipulate it. This was going to be possibly the only chance anyone would have to demonstrate the tamperability of these systems. So what I did was I went downstairs to teach my graduate level security class that I was teaching at the University of Michigan that term. And I faced a problem, which was that I had no idea how to build a circuit board that we could put into one of these machines. So I asked the students whether any of them knew how to build a board. This guy, Eric Woostrow, who was a senior at the time, sheepishly raised his hand to volunteer. When I told him we only had 3 days, he looked at me like I was crazy, but he still agreed to do it. And partly for that reason, Eric is now one of my PhD students, and he's been a big help in the preparation of this course. Another problem with any kind of attack that's going to involve tampering with the electronics in the machine is that you'll have to have physical access to them. Now, you can think of various ways that a criminal could get that kind of access. Maybe the criminal is an election insider. We've talked about insider attacks and why they're a huge threat already. Another possibility is that the attacker could try to manipulate the machines between elections while they're in storage. In India, these EVMs are kept in vast warehouses that might have thousands of machines in one place. They're usually not in the highest security facilities. They might be part of a high school or an old industrial facility. You can easily imagine how criminals might be able to bribe or coerce the guards to get into one of those warehouses when they'd then be able to tamper with thousands of machines in one shot. The Indian machines are also protected with tamper-evident seals, but they're not the highest tech kinds of seals. You can see a couple of pictures of them here. The seals on the machines consist of candle wax, paper, and string, and I'm sure all of you can think of some ways you might be able to tamper with these. So Rob and I got to Hyderabad and proceeded to test out the board Eric had built on the real machines. And it worked almost on the first try. So here's the board Eric built. It looks almost exactly like the real display board found in the Indian EVMs, except underneath these LEDs and that plastic spacer, we've added some additional components. On the left, you see that square chip. That's an embedded microcontroller, a microprocessor. What it does is it intercepts the signals the machine is trying to send to the board to tell it which results to display, and it can rewrite them on the fly. This is what we call a man-in-the-middle attack, but it's implemented in the electronics of the board. We call this attack a dishonest display board, and the dishonest display can replace the real results with whatever results the criminal wants to show. Here's a picture of the dishonest display inside the real EVM. And here's a comparison between the regular display board and the dishonest board. A simple inspection is not going to reveal any differences. The way the board works is it watches when votes are being counted and moves votes from all the other candidates to the preferred candidate of the attacker. This is a little bit tricky because we have to make sure the total still adds up to the right number. Otherwise, if they're just counting the number of voters, they might detect the attack. But we were able to do this with some clever software heuristics. So you might imagine that attackers who took over a warehouse or something would replace the real boards with dishonest displays in thousands of machines, but that's a lot of effort to go to for just one election. If they wanted to leave the boards there and cheat potentially in all future elections, they'd need some way to tell the board which candidate number to favor. You won't be able to predict years in advance which ballot position your candidate will be on, but you will then need some way to communicate to the board who to cheat for. So there are several ways you could do this in the Indian system, but the one that we actually demonstrated involves that other chip to the right of the M. That's an embedded Bluetooth radio, and it talks to an application on a smartphone. So we built this prototype application that lets you control the dishonest display. It lets you pick which candidate you want to win and what fraction of votes to shift to them. So someone could be at that counting session in public where they're holding up the machines and use a smartphone with an application like this to signal to all the dishonest displays who should win. The second attack that we demonstrated has to do with these chips. These are the memory chips that record the votes and vote totals inside the machine. Harry and his team of engineers had reverse engineered the data format, the structure of the information stored on these chips, and they were able to find out that there was no cryptographic protection to the information stored on them. They were able to come up with an attack where if you hooked a laptop up to the voting machine, you could rewrite the votes to reflect whatever totals you wanted. But this wouldn't be very practical in the field. It takes maybe 15 minutes per machine to set up and requires bulky, sensitive equipment. So we consulted with the team in Hyderabad after I was back in Michigan, and we came up with a design for a new attack that would be a much more compact form of manipulating the votes in the memory chips. This is what we built, and I'm holding one of these devices right here. This is a device we call Clippy. Clippy attaches directly to the memory chips inside the voting machine, and with the machine powered on, it rewrites the votes stored in the chip to be in favor of whichever candidate the attacker wants. You just turn this knob here on top of the device to pick the candidate you want, attach it to the chip, and then the busy light comes on and flashes orange for a couple of seconds. Then the done light lights green to let you know you're finished. You detach the device, move on to the next machine. So Clippy represents an electronic form of the booth capture attack. If the criminals can take over a polling place, they can open up the machine and stuff as many ballots into the ballot box as the virtual ballot box as they want using a device like this. These are low cost. They would cost just a few tens of dollars to make. They are simple electronics. There are probably 1 million people in India who could make one. And they are so simple to use, you could have your uneducated goons carry out the attack. So either during the polls or during that time between when votes are cast and counted, which can be a couple weeks in India, an attack like this could manipulate all the votes stored in the machines. Then there's one more security issue that leads to some other possibilities of attacks you might have thought of. And that has to do with that secret software that's baked into the chip, the actual software that's counting the votes. How do we know the software in the machines is honest? Well, it turns out that there are several impediments to being able to trust that software. First of all, the Election Commission of India, the country's highest election authority, doesn't own the source code. The software is owned by the companies that made the machines. Second, the Election Commission has never even seen what's in the source code. They're just taking it on the word of the engineers who developed it. One of the Election Commission's chief technical experts told me that only 3 or 4 guys at the companies that made the machines know what's in the code. But he says there's nothing to worry about because he's talked to those guys and they seem trustworthy. You can imagine that those engineers, even if they are trustworthy, they might be bribed, they might be coerced, someone could threaten them or their families in order to try to smuggle in some vote-stealing code into the chips. But because the chips are implemented in a way that makes it virtually impossible to read out the code after the machines are in the field, there's no way to tell whether the software that's actually in them matches what's supposed to be running or whether the software inside them is honest. This just means there's no transparency whatsoever to the process of counting votes in these machines. It creates a tremendous threat for possible dishonest software corrupting the election results. So our study concluded that the paperless EVMs used in India are, in fact, tamperable and insecure. Committing fraud with the EVMs would take basic electronic skills, not rocket science. And this kind of fraud could take place either while the machines are in storage, during polling, or between polling and counting. Detecting fraud with these attacks could be difficult or impossible, especially if they were carried out with the help of dishonest election insiders. For these reasons, we concluded that the Election Commission's claims that the machines were perfect, tamper-proof, and in no need of technical improvement were totally without basis. We'll see how the Election Commission responded to these findings in the next segment.